Welcome to the presentation on defining components and modules in high-level design. In this session, we will explore the critical aspects of system architecture, breaking down a system into manageable, scalable components and understanding how they interact to form a robust solution. Let's dive into the world of high-level design. High-level design focuses on structuring the core components of a system and ensuring that each part plays a distinct, scalable role. We start by breaking down large systems into manageable chunks, components, and modules, making it easier to develop, test, and maintain the system in the long term. Now, let's define what components and modules are in HLD. A component is a larger unit within the system responsible for specific functionality like payment processing or user management. A module is a smaller part of a component designed to handle a specific task within the larger functionality. These elements communicate with each other to form a cohesive solution. Let's look at the different types of components that make up a system. We have front-end components that focus on the user interface and user experience. Back-end components handle the business logic, including processes and data manipulation. Database components manage data storage. External services like third-party payment gateways integrate outside services. Security components handle authentication and encryption, while infrastructure components manage deployment and scaling. Finally, analytics components track system performance and user behavior. Front-end components are crucial because they form the interface between the user and the system. They are responsible for the design and usability of the application. Technologies like HTML, CSS, JavaScript, and frameworks like React or Angular are used to build these components. The backend is the backbone of our system, handling the business logic and data processing. This is where things like user authentication, transaction processing, and other critical operations happen. Common technologies for backend components include Node.js, Python, Java, Ruby on Rails. Database components are responsible for managing data, whether it's user information, transactions, or other system-related data. Relational databases like MySQL or PostgreSQL are often used for structured data, while NoSQL databases like MongoDB are used for flexible, unstructured data. External service components integrate third-party services into the system. This can include services like payment gateways, Stripe, PayPal, communication APIs, Twilio for SMS, or even cloud services. These components allow the system to scale and leverage features not implemented internally. Security components are designed to protect our system and users. They handle tasks like user authentication, ensuring that only authorized users can access certain features, and encryption, which protects sensitive data during transmission and storage. Technologies like OAuth2, JWT, and SSL/TLS are commonly used in security components. DevOps and infrastructure components focus on deployment, scaling, and maintaining system health. They ensure that the system remains functional as user demand grows. CI/CD pipelines, containerization tools like Docker, and orchestration platforms like Kubernetes are commonly used in this area to automate deployment and ensure reliability. Analytics and monitoring components help track system performance and user behavior. These components collect data about how the system is functioning and provide insights into areas that need improvement. Tools like Google Analytics, Grafana, and the ELK stack are widely used for real-time monitoring and error tracking. When defining components in our system, it's essential to keep several considerations in mind. Modularity ensures that components can evolve independently. Reusability minimizes code duplication. Loose coupling ensures that changes in one component don't affect others. Scalability allows components to grow the system, and clear communication defines how components interact with one another. Let's look at an example of components in a real world system, a typical e commerce platform. The front end handles the product catalog, shipping cart, and checkout process. The backend manages order processing and inventory. The database stores user data and transaction history. External services handle payments, and security ensures data protection and user authentication. DevOps takes care of deployment while analytics monitor the performance of the platform. In conclusion, defining components and modules is vital in high level design to create a modular, scalable, and maintainable system. By proper breaking down a system into well defined components, we ensure that each part can evolve and scale independently, contributing to a robust and efficient architecture. Thank you for your attention. This concludes the presentation on components and modules in high level design. If you have any questions or would like further clarification on any of the topics discussed, feel free to ask now. Welcome to day 16 of our high level design course. In this session, we will dive into breaking down components and services. Let's explore how to effectively decompose complex systems into manageable, scalable parts and define clear service boundaries. Here's our agenda for today. First, we will discuss how to decompose large systems into smaller, more manageable components. Then, we will explore how to identify service boundaries. Finally, we will cover tools and techniques that help us in the decomposition process and in defining boundaries. When breaking down a large system, functional decomposition is a great starting point. We break the system into subcomponents based on their functionality. This makes the system easier to understand and work on. Next, we follow responsibility driven design, where each component is given a clear singular responsibility. By doing this, we keep our components focused and manageable. Lastly, we need to balance the size and scope of each component. If a component is too large, it becomes too complex to maintain. If it's too small, it might create unnecessary overhead. Core components are central to the operation of the system. For example, in an e-commerce platform, payment processing, order management, and user authentication are core components. Peripheral components like logging and analytics support the system but aren't critical to its main function. When designing, prioritize the core components and focus on them first to define the overall structure of the system. Service boundaries define where one service ends and another begins. This is crucial for modularity. By clearly defining service boundaries, we ensure that different parts of the system can operate independently and scale as needed. For instance, in an e-commerce system, the payment service might interact with inventory, but these separate services that should be loosely coupled. Microservices architecture is a common approach to defining service boundaries. Each microservice encapsulates a distinct business capacity, making it easier to scale and maintain. It's important to avoid overlapping services to minimize tight coupling. By having clearly defined service boundaries, we reduce complexity and increase flexibility in scaling and development. In domain-driven design, we use bound contexts to define service boundaries. A bounded context represents a specific domain within the system where a particular model applies. For example, the customer in the user service might be represented differently than the customer in the billing service. This allows us to model complex business domains effectively while maintaining clarity and avoiding confusion. We also need to distinguish between external and internal boundaries. External boundaries are points where our system interacts with outside systems like third-party APIs or databases. Internal boundaries define interactions between internal services such as between the front end and back end or between different microservices. Once we have broken down the system into components, it's essential to define how they communicate. This is done through well-defined communication interfaces, usually in the form of APIs. It's important to design these APIs thoughtfully, ensuring backward compatibility and versioning to prevent issues as the system evolves. We also need to map out service dependencies to identify potential bottlenecks or scaling issues. Service dependency mapping helps us understand how different services are interconnected. By defining these dependencies, we can make sure that critical services don't fail when others are down. For example, if the payment service depends on the inventory service, we need to ensure that the payment service can handle failures in inventory gracefully without causing major disruptions. Let's take an example of a service boundary in an e-commerce system. We might have a user service that handles authentication and profile management. A separate product service would manage the product catalog, while an order service is responsible for order processing. These services should interact with one another through clearly defined interfaces such as APIs or event driven systems. To help with decomposition and defining boundaries, we use different architectural styles and tools. Microservices, event driven architectures, and modular monoliths are some of the styles we can apply based on the complexity. Tools like UML and C4 models help visualize the system structure while maintaining cohesion within components and reducing coupling between them. In dynamic systems, we use service discovery tools like Consul, Eureka, and Kubernetes. These tools help manage service boundaries in environments where services are constantly being added, removed, or scaled. Service discovery ensures that services can find and communicate with each other without manual configuration, making the system more flexible and adaptable. In conclusion, breaking down components and defining service boundaries is critical for creating scalable, maintainable, and flexible systems. Focus on clear responsibilities for each component, reduce dependencies between services, and design APIs for smooth communication. By following these principles, we can build systems that are easy to scale and evolve. Thank you for your attention. If you have any questions or need clarification, now is the time to ask. I would be happy to discuss any points further. Welcome to day 17 of our high level design series. Today we will be diving into the topic of data flow and state management in distributed systems. We will explore how data moves through components and how state is maintained across different services. Let's start by understanding the key concepts. Data flow refers to the movement of data between system components, while state management refers to how a system tracks and synchronizes its state across services, especially in a distributed environment. One of the first things we need to do when designing data flow is create data flow diagrams or DFDs. These diagrams visually represent how data moves through the system. Additionally, using a layered architecture helps in organizing the system. For example, the presentation layer, the business layer, business logic layer, and the data access layer, where each layer has a distinct responsibility. A pipeline architecture such as ETL, extract, transform, load, also helps ensure a smooth data flow. Next, let's differentiate between synchronous and asynchronous data flow. In synchronous data flow, tasks are executed in a sequential manner with an immediate response expected. This is great for real-time data updates. On the other hand, asynchronous data flow allows tasks to run concurrently, ideal for event-driven systems like when using message queues. An API gateway plays a critical role in managing data flow in distributed systems. It acts as the central hub, routing requests to appropriate services. It helps centralize control, making it easier to manage traffic between different components of the system. Now let's discuss state management. In stateless systems, there's no memory between requests, which makes them scalable but limited in scenarios like user sessions. In stateful systems, state is retained between requests, which is useful for maintaining user sessions, shopping carts, and other long running tasks. When we talk about session management in stateful systems, we commonly use methods like JSON Web Tokens or JWT and session cookies. These store state information such as user sessions, which are then retrieved on subsequent requests. This helps ensure continuity for users across multiple interactions. Event sourcing is a pattern where every state change in the system is captured as an event. This allows us to rebuild the system state at any point in time. Coupled with CQRS, command query responsibility segregation, we separate commands from queries, optimizing read and write operations to better suit different use cases. To enhance performance, distributed caching solutions like Redis and Memcached can be employed. These caches store frequently accessed data closer to the user, thus reducing latency and improving response times for critical data requests. Data replication is a key strategy for ensuring high availability and fault tolerance. By duplicating data across multiple servers, we ensure the system remains operational even if one server fails. About consistency, we have models like eventual consistency, strong consistency, and the Cape theorem, which addresses trade-offs between consistency, availability, and partition tolerance. For managing stateful services, orchestration tools like Kubernetes stateful sets are critical. They allow for the proper management of services that need to maintain state while ensuring high availability and consistency across the system. Message queues such as Kafka and RabbitMQ are great for handling asynchronous state updates. They allow services to trigger events which propagate state changes across various components of the system. This ensures that the system remains consistent while decoupling services. While implementing data flow and state management, we face several challenges including latency, consistency, error handling, and scalability. To mitigate this, we often use parallel processing, retries, circuit breakers, and horizontal scaling to keep the system running smoothly even under heavy load. In conclusion, managing data flow and state is crucial to the success of distributed systems. By using tools like caching, API gateways, and event-driven architecture, we can handle complexity and build scalable, reliable systems. Proper data flow and state management ensure that services operate cohesively and efficiently, delivering a seamless user experience. Hello and welcome to today's presentation on communication between components. In this session, we will explore the different types of communication methods used in distributed systems, including synchronous and asynchronous communication, and look at communication protocols such as REST APIs, gRPC, and messaging queues. Communication between components is a critical part of designing scalable and efficient distributed systems. The main types of communication we will focus on are synchronous and asynchronous communication. Additionally, we will discuss key technologies such as REST APIs, gRPC, and messaging queues, all of which play a vital role in how components interact with one another. Let's dive into the two main types of communication, synchronous and asynchronous. In synchronous communication, the sender waits for a response from the receiver before continuing with the process. This type is ideal when immediate feedback is required, but it can create issues if the receiver is slow or unavailable, as it blocks further operations. On the other hand, asynchronous communication allows the sender to continue without waiting for a response. This approach is non-blocking and highly scalable, making it well suited for tasks that don't require immediate responses like event-driven systems or background tasks. Now, when deciding between synchronous and asynchronous communication, it's important to consider your system's needs. Use synchronous communication when immediate feedback is essential, like in real-time applications where tasks must happen in a specific order. On the other hand, asynchronous communication is a better choice when scalability is a priority. It allows components to operate independently and can handle large volumes of messages without blocking the system. Next, let's talk about REST APIs, one of the most common communication methods used in web and mobile applications. REST stands for Representational State Transfer and it follows a stateless architectural style. Communication happens via standard HTTP methods such as GET, POST, PUT, and DELETE, with data typically exchanged in JSON or XML formats. Another popular communication protocol is gRPC. Developed by Google, gRPC is a high performance remote procedure protocol (RPC) framework that uses HTTP2 for faster communication. What makes gRPC stand out of its use of protocol buffers for serialization? which is highly efficient and strongly typed. gRPC also supports bidirectional streaming, enabling real-time communication between services. This makes gRPC an ideal choice for microservices architectures or applications that require low latency and high throughput, like chat applications or live data feeds. Messaging queues play an important role in asynchronous communication by allowing components to communicate through queues without needing to be directly connected. Two common messaging queues are Kafka and RabbitMQ. Kafka is designed for high throughput data streaming and real time analytics, while RabbitMQ is a message broker that supports various protocols including AMQP. When deciding on a communication protocol for our system, several factors come into play. If real time processing is essential, protocols like gRPC might be the best choice. For simpler web-based interactions, REST APIs are often preferred. On the other hand, if we need decoupling and asynchronous message processing, a messaging queue like RabbitMQ or Kafka might be the best solution. Effective failure handling is essential in any distributed system. Let's look at a few strategies. First, timeouts can be used to handle delays in communication, triggering retries or providing failure responses when a service is unavailable. Automatic retries can help ensure that requests are retried if they fail temporarily. The circuit breaker pattern helps prevent repeated failed requests to an already failing services. With dead letter queues, store failed messages for investigation and further action. In conclusion, communication between components is crucial for the proper functioning of distributed systems. Choosing between synchronous and asynchronous communication depends on factors like performance needs, and system scalability. Using REST APIs, gRPC, and messaging queues can help meet different communication requirements. Additionally, implementing failure handling mechanisms like retries and circuit breakers ensures that the system remains resilient and reliable. Thank you for your attention. I hope this session will provide valuable insights into the communication strategies used in distributed systems. If you have any questions or need further clarification, feel free to ask. Hello and welcome to today's presentation on integrating external services in high-level design. This is day 19 of our series where we will dive into how to integrate third-party services, handle failures, and ensure security when working with external APIs and systems. Let's take a look at the agenda for today. We will begin with an introduction to third-party integrations, followed by common types of integrations. Then we will explore how to design these integrations in a high-level design before discussing failure handling and retry mechanisms. Finally, we will cover the essential security considerations when integrating external services and wrap up with some best practices. External services significantly enhance the capabilities of our system by providing specialized functionalities that would otherwise require substantial development effort. Common examples include payment gateways like PayPal or Stripe, external APIs such as weather or social media APIs, and services like messaging or authentication providers. By using third party services, we save time, leverage industry expertise, and depend and expand our system's features without reinventing the wheel. Let's take a closer look at some of the common types of third-party integrations. Payment gateways such as PayPal or Stripe are crucial for handling online payments. External APIs can provide a range of functionalities like weather updates or access to cloud storage, for example AWS or Google Cloud. Messaging service like Twilio for SMS or SendGrid for email enable real-time communication, while authentication services such as Oath and SSO simplify user authentication. When designing third-party integrations in high-level design, it's essential to clearly define the interfaces. This includes the API endpoints, expected data formats, and response structures. Additionally, we must consider authentication and authorization processes such as API keys or auth tokens. Service availability is another key factor. We need to account for how the third party service may affect our system if it's down or unavailable. No system is perfect and external services can fail. It's important to anticipate failure scenarios such as timeouts, rate limits, or service outages. To address this, you can implement retry strategies like exponential backoff, where retries occur at increasing intervals. A circuit breaker can also stop retries after a number of failures, preventing our system from being overwhelmed. Setting timeouts and grace periods helps manage response expectations, and fallback mechanisms can switch to alternative services if necessary. Monitoring and altering mechanisms are crucial for tracking failures and notifying administrators. In our HLD, be sure to define the retry strategies, including the number of retries and the backoff interval. A circuit breaker pattern will allow us to stop retries once failure thresholds are reached, avoiding additional strain on our system. Logging is critical. Detailed error logs will help track integration issues and make troubleshooting easier. Security is a top priority when integrating third-party services. We should securely store API keys and sensitive credentials using environment variables or encryption. Ensure all communications between our system and external services are encrypted using HTTPS or SSL TLS. Implement OAuth or token-based authentication to safeguard access to APIs, and always validate and sanitize inputs to prevent injection attacks. Also follow the principle of least privilege when setting access controls to minimize exposure to sensitive data. Security considerations in HLD must include how authentication is managed, ensure tokens are securely stored and used, encryption should be applied to all sensitive data exchanged between systems. Additionally, define clear access controls specifying who has access to the third party services and under what conditions. To summarize, robust integration is key. Define clear interfaces, plan for failure recovery, and make security a priority. Retry mechanisms such as exponential backoff and circuit breakers should be part of our design to handle failures gracefully. Always follow best practices for security by securing credentials, validating data, and using encrypted communication channels. Regular testing and monitoring are also crucial to ensure smooth operation of external integrations. Thank you for your attention. I would now like to open the floor for any questions you might have. Feel free to ask about the integration strategies, failure handling techniques, or security practices we have discussed today. Welcome to the presentation on data storage strategies. Today we will explore the differences between relational and NoSQL databases and help us understand how to choose the right data storage solution for our system. Data storage is a critical component in system design. The right choice of storage solution can directly impact our system's performance, scalability and data integrity. Today we will discuss two main types of data storage: relational databases and NoSQL databases. Relational databases, also known as RDBMS, store data in tables with rows and columns. They use SQL for querying and managing data. One of the key features of RDBMS is the ACID properties: atomicity, consistency, isolation, and durability, which ensure data integrity and reliability. Popular examples of RDBMS include MySQL, PostgreSQL, and Microsoft SQL Server. RDBMS are designed to handle structured data that follows a predefined schema. They are well suited for complex relationships and transactional systems, providing guarantees through ACID properties. These databases are ideal for use cases like financial systems and customer relationship management. Unlike RDBMS, NoSQL databases are designed for flexible and scalable storage, especially for unstructured data. There are several types of NoSQL databases, including document-based, key-value stores, columnar databases, and graph databases. These databases emphasize horizontal scaling and often provide eventual consistency. NoSQL databases come in several types. Document-based databases like MongoDB store data in formats such as JSON or BSON. Key-value stores like Redis are optimized for simple lookups. Columnar databases like Cassandra are best for handling large-scale analytical queries. Finally, graph databases like Neo4j model data as nodes and relationships, making them suitable for complex queries such as social networks. One of the main advantages of NoSQL databases is their flexible schema, which allows for easy changes as the application evolves. They also excel at horizontal scalability, allowing systems to scale by adding more servers. NoSQL is ideal for applications that require real-time analytics, IoT data management, or social network data storage. Choosing the right database depends on several factors. For structured data, relational databases are a natural fit, while NoSQL databases work better for unstructured or semi-structured data. We will also need to consider scalability, consistency, and performance requirements when making our decision. RDBMS typically excels at handling complex queries, where NoSQL databases shine with high throughput and flexible data models. In modern systems, many developers adopt a hybrid approach using both RDBMS and NoSQL databases. This strategy, known as polyglot persistence, allows us to use the strength of both systems. For example, we might use an RDBMS for transactional data like user accounts, while NoSQL handles unstructured data such as logs or social media posts. When choosing a storage solution, it's important to consider factors such as data volume, access patterns, and redundancy. For example, if our application requires complex transactions and RDBMS is likely the better choice. On the other hand, if we are dealing with large volumes of unstructured data or need to scale horizontally, NoSQL might be more suitable. In summary, both relational and NoSQL databases have their strengths and weaknesses. RDBMS are ideal for structured transactional data, while NoSQL databases excel in flexibility, scalability, and handling unstructured data. A hybrid approach can offer the best of both worlds, providing us with a robust and scalable architecture. Thank you for your attention. If you have any questions or need any clarification on any of the topics we covered today, please feel free to ask. Welcome to this presentation on security considerations in high-level design. Today we will discuss key security concepts including authentication, authorization, encryption, and secure data handling, all crucial for building secure systems. Let's dive in. Security is an essential aspect of system design, ensuring that the system is protected against threats and vulnerabilities. The key areas we will focus on include authentication, authorization, encryption, and secure data transmission and storage. By the end of this presentation, we will have a solid understanding of these security considerations and how to implement them in our high-level design. Authentication is a process of verifying a user's identity. Common methods include password-based authentication, where users provide a password to access the system, and multi-factor authentication (MFA), which requires multiple forms of identification like a password and a text message code. We also have OAuth and OpenID Connect for secure token-based authentication and biometric authentication, which uses unique physical characteristics like fingerprints or facial recognitions. Once users are authenticated, authorization determines what they are allowed to do within the system. Role-based access control or RBAC grants permissions based on roles such as admin or user. Alternatively, attribute-based access control or ABAC provides more granular control by evaluating specific attributes such as department or clearance level. By setting proper permissions and access policies, we ensure that users only have access to the resources they are authorized to use. Encryption is a critical technique to protect sensitive data. We can apply encryption at rest to protect data stored on disk, ensuring it remains secure even if unauthorized parties gain access to the storage. Encryption in transit secures communication between clients and servers, preventing end-to-end encryption used in messaging systems ensures that only the sender and recipient can read the message even if it's intercepted. To secure data transmission, we use protocols like SSL, or TLS, which encrypt data exchanged between web servers and clients. This ensures the confidentiality and integrity of the data. When dealing with APIs, it's essential to secure them using protocols like OAuth 2.0 for authentication and access control. Data integrity can be maintained using hashing and digital signatures, ensuring that the data hasn't altered during transmission. Data storage must also be secure. Encryption at rest ensures that even if attackers gain access to the storage, they cannot read the data. Database security practices such as access control and encrypting sensitive fields like passwords or credit card information are critical. Additionally, techniques like data masking and tokenization protect personally identifiable information (PII) by obscuring sensitive data while still allowing it to be used for legitimate business purposes. In distributed systems, security becomes even more complex. Identity and access management (IAM) is vital for ensuring that users and services are granted appropriate permissions. Federated identification management allows users to authenticate across different domains or services. Service to service security can enforce using mutual TLS, MTLS, API gateways, or service meshes, ensuring that communication between microservices is secure and authenticated. Security testing is an ongoing process. Static application security testing (SAST) and dynamic application security testing (DAST) are used to identify vulnerabilities in the code and runtime environment. Penetration testing simulates real-world attacks to evaluate the system's defenses. Third-party security audits offer an external perspective on system security, ensuring that vulnerabilities are properly identified and addressed. Once the system is deployed, continuous monitoring is necessary to detect any suspicious activities. Centralized logging aggregates logs from all system components for analysis. Real-time monitoring helps identify potential threats early. An incident response plan outlines how to detect, contain, and investigate security breaches, ensuring that any security issues are swiftly handled. When designing a secure high-level architecture, several best practices must be followed. Always encrypt sensitive data, use the principle of least privilege to limit user access, and conduct regular security audits. Secure communication protocols such as TLS and HTTPS must be used to protect data in transit. And finally, it's crucial to have a solid incident response and monitoring plan to quickly address any security issues. In conclusion, security must be foundational element of our high-level design process. Authentication, authorization, encryption, and secure data management ensures the integrity and safety of our system. Remember, security is not a one-time task, but an ongoing process that needs continuous attention and improvement. Thank you for your attention. If you have any questions or need clarification on any points, feel free to ask. I am happy to help.